Hello, welcome back to my channel. I'm glad to have you here. Today I want us to look at the continuation of our previous lesson, current electricity. But today I want us to look at the resistors. And of course we can have that resistors are opposition to the flow of current, or we can say that yes, a resistance is an opposition to the flow of current. Resistors, we can have the arrangement of resistors. Our resistors can be arranged either in series or in parallel. Then we have number one, resistors in series. Resistors in series. And when the resistors are connected in series, we can have this, we can have it like this, and we can have it like this. Assuming there are three resistors that are connected in series, then here we have the potential difference, here V. Then here is R1, R2, R3. Now if we have these, then this is the direction of the current flow. Okay, but just before we start, please, if you have not subscribed to this channel, do me a favor, hit the subscribe button, hit the like button, and then share this video with your friend. Now let us go. Now we said that if we have these total resistors in a series will give us that, yeah, total resistor, which is a R. We can say R subscript T, which is a R total. Now R total will give us R1 plus R2 plus R3. Now if you have this is how we can calculate the resistors in series. Now there are three things I want us to note here. Three things I want us to note here, that yes, if you have this type of connection, the total resistor is this. Then first thing I want you to note that if we have this connected like this, since it is in series, the same current flows. Now the same current flowing into R1 will flow into R2, and the same current will still flow into R3. And that is the first one. The second one is that the potential difference V is dependent on the value of the resistors here. For example, assuming we have here to be, okay, let me leave the here. Assuming we have here to be 2 ohms, maybe here is 3 ohms, maybe here is 1 ohm. Potential difference here depends on the value of this. So since R1, R2, R3 have different resistors, this one will now draw the PD equivalent to its value. This one will draw PD equivalent to its value, and this one will draw PD equivalent to its value. Therefore, at the end of the day, we now have that the potential difference here is equal to V1 plus V2 plus V3. Now we have the resistors in parallel. Now if resistors are in parallel, connected in parallel, you can have something like this. Though there are different ways of connecting resistors in parallel, we are going to x-ray some of those ways of connection in parallel. Now I want you to note that yes, once you get here, there is a junction here. There is another junction here. Now if current is flowing, maybe this is I. If current is flowing, on getting to this junction, it will split. Some will flow in this direction towards R1, some will flow in this direction towards R2, and then some will flow in this direction towards R3. So in other words, we can have here as I1 here, maybe we can have I2 here, and then we can have I3 flowing here. Now here, total resistor or total resistance in the circuit, because this is a parallel connection, we can have 1 over R, we can have 1 over R total here, giving us 1 over R1 plus 1 over R2 plus 1 over R3. Now, once we have this, or with it as, yes, R total here, giving us, let's say, R1, R2, R3 all over R1, R2 plus R3. We can have it so either you have it in this form or you have it in this one. I want us to note, there are 2 or more things I want us to note here. 1, because this is connected in parallel, the same voltage or the same potential difference is flowing through. The moment it gets this one, the same PD is flowing, which is in contrast with the other one with series. So in parallel, you have that V is equal to V1, which is equal to V2, which is equal to V3. That means the same current flowing in the same PD flowing in V1 is the same PD flowing in V2, and the same PD is flowing in V3. Now, the second thing I want us to note here is that since the current here is highly dependent on the value of the resistor, that means if, let's say, R1 is 5 ohms, R2 is, let's say, 2 ohms, and then R3 is, say, 3 ohms, different currents will flow. But at the end of the day, by the time you add 1, 2, 3, it will give you this. Therefore, we now have that total current in the circuit will give us I1 plus I2 plus I3. Okay. The third thing I want us to note here is that by the time you use this formula to resolve these resistors, or you use the one to resolve it, total, as we will have R1 5, this one 2, this one is 3, the total resistors in the circuit will be less than the smallest value. Of course, there are 3 resistors there. The least is this. By the time you add all of them, it will give you a value smaller than 2. So these are the 3 main things that I want us to look at now. Having discussed this, let us use some questions to add value to this. But before we do that, we now know that from Ohm's law, of course, Ohm's law states that yes, current passing through a metallic conductor, e.g. wire, is directly proportional to the PD across the terminals of that wire, provided the temperature and other physical factors are kept constant. So in other words, we can have that V is equal to, or V is proportional to I. Now we now have that V is equal to IR. By the time you make I the subject here, from here we can now have that I is V over R and vice versa. So if you want to make R the subject, R will now give you V over I. Okay. Now let us take some questions here. Okay, we have the question on the board, and this question says, from the circuit above, from the circuit above, calculate 1 if effective current, effective resistance in the circuit, II, the potential difference, the potential difference in the circuit. All right, solution. if we look at this question, the diagram is a combination of series and parallel. This side is parallel, while this side is a series. Now, all we need to do is resolve this one that is in series, in parallel first. By the time we resolve it, it will now be in a series with this, and then from there we can proceed. Now, solution. So we have the first thing we'll do is total resistance in parallel. Total resistance in parallel will give us, and of course, it's either we use the longer formula or we use the shorter formula, which says R is equal to R1, R2 all over R1 plus R2. Now, it will now give us that the ones in series, of course, we can have this one as R1, we can have this one as R2. However you want to take it. So to now be R1, we can have 2, of course, you know that this thing means multiplication. So R1, 2 times R2, which is 4, all over R1, which is 2 plus 4. It will give us 2 times 4 will give us 8. 8 over 2 plus 4 will give us 6. Therefore, R will give us 8 over 6 will give us 1.8 divided by 6 will give us 1.3 ohms. 1.33 ohms. That is the one in the parallel. Now, the second one we say total resistance in series. The one that is in series will give us R equals R1 plus R2 plus R3. Remember, this one will now be in series with this. So all we need to do is we'll say R1 is 5 plus R2, which is 10, plus R3, which is the whole of this. The whole of this will now give us 1.3. At the end of the day, we now have that the resistance in the circuit will give us, of course, 5 plus 10 is 15 plus 1.3, which will now give us 16.3 ohms. And this is the resistance we have here. Now, of course, this is the first question. The second question says the PD in the circuits. Now, the PD in the circuits will now give us, of course, because we have resolved it. So the same PD flows. Now, the current flow in the circuit is I is equal to 0.5 ampere. Now, R is 16.3 ohms. Now, what will V give us? Now, V will now give us, from Ohm's law, we'll have that V is equal to IR, which will give us I, which is current, 0.5 times 16.3. Therefore, V will give us 0.5 times 16.3. It will give us 8.15 volts. The potential difference flowing in the circuit. Alright, let us take another question. Okay, we have this question before us here, and the question says the total resistance measured at PQ in the diagram is dash. This is a JAMB question. It must be either this, or that. Now let us find out which is the correct option. Now we have here, if you take a look at this, this, of course, when you see this type of node here, it means that this is just section of a particular circuit. Now, from here now, we can have that these two, in fact, the whole of 1, 2, 3, are in series to this one. They are in series. And because of this, there is a junction here. You should note this. Anytime you see this type of connection, that means there's a junction here. It means that you can always pull this side off. 1, 2, 3 are in series. You can always pull it off. And then when you pull it off, the remaining 1, 2, 3 will now be it's 1, 2, 3 are in series. 1, 2, 3 are in series. So how do we solve this? Gradually you reduce them. So you pull 1, 2, 3. So we can call this one R1. We can call this one R2. We can call this R3. So solution, we have said that R1, R2, and R3 are in series. So if they are in series, we will resolve it. So I want to divide the board into two. So we will resolve it. Now if we resolve it, we now have that total resistor in series will give us R equals R1 plus R2 plus R3, which will give us R with 2 plus 2 plus 2. 2 plus 2 plus 2 will give us 6 ohms. Now, having resolved this, we have a single value now, which is this. That one will now be, we will redraw these circuits. If we redraw the circuits to now come, it will now be in parallel with this one now. So because of it now, we will single this one to now be in parallel with this. So when we do that, we have, if we redraw the diagram, we have this. Now this is that junction. We put this resistor here. Now the other one, we have the other one like this, and then this one. So 1, 2, 3. This is it. Still P and Q. Now this one that we have resolved to give us a single value, we can bring it and then add it. So if we bring it, this is the picture of what we have. So this will now be the picture of what we have. So here we still retain here as our 1 ohm. Here we retain it as 1 ohm. This one is still 3 ohms. Now the whole of this, which is down this value now, is 6 ohms. Now if we do this now, look, if we take a look at this, we discover that of course these two are now in parallel. So if they are in parallel, we will resolve it. Once we resolve it, it will now be in series with this. Then we can now add. So we can now say, since 3 and 6 ohm are 3 ohm, and 6 ohms are in parallel. Since they are in parallel, we can have that R is equal to, we can say R total is equal to R, what we label it, since here is R1, R2, R3, we can say here is R4 here, and then here we can call this one R5. So we can now have R4 multiplied by R5 all over R4 plus R5. Now when we do that, we will now have R4, which is 3 times R5, which is 6, all over 3 plus 6, and it will give us that the R total is equal to 3 times 6 is 18, all over 3 plus 6 will give us 9, and then this over this will give us 2 ohms. So having resolved this, we can now redraw this also. We can redraw this. Because this and this will not give us. So when we redraw it, it will not give us this, and this. So we have it like this. This is the resistor, and down here and have another one here. Then this one will give us like this, and then we come down here. So here we still retain 1 ohm. Here we retain 1 ohm. Then here we retain 2 ohms. At this point now, it is obvious that this is a series connection. Because this is series connection now, we can, of course, the series connection is just this plus this plus this. It will now give us okay, just permit me to write here. So we now have that our resistance in series is equal to R1 plus R2 plus R3, which will give us, we can take this one as our R1, take this as our R2, take this as our R3. So which will give us 1 plus 2 plus 1. Therefore, R will give us 4 ohms. Do we have 4 ohms among the options there? Yes, option C is the correct answer option. So, once you have this type of question, take it slow and steady. You will get it. And let us take one more question before we leave. We have this question. The question says, the sum of the current in the figure below is this and that. Now, if you take a look at this figure, we have this figure is a combination of series and parallel. If you remove these 10 here, what you have remaining is series. If you leave it like this, you have series here, both series and parallel. Now, different currents are flowing from here. So, of course, from here now, current is from this potential, from this voltage here. We have I2 just for this one, I1 just for this. How do we solve this? Now, there are 2 ways of solving it. So, it's either you first calculate the resistance in the circuit, and then you now calculate it all over the potential difference, or you can calculate for I1 first. If you are calculating for I1 will give us, and of course, if you are calculating for I1, there are 2 resistors here. These 2 resistors are in series. So we now have for I1 first, resolve the total resistance, which will give us R is R1 plus R2, which will give us 5 plus 10, which will give us 15 ohms for just this one. Now, the same, remember what we said, that if you have series connections, same PD flows. Now, V will give us 12 volts. So, we now have from Ohm's law, we have that V is IR, so that I or I1 will give us V all over R. Now, it will give us, I1 will now give us V, which is 12 over R. Total R here is 15. And then it will give us 12 divided by 15 will give us 0.8 ampere. Now for I2, we have that the only resistor we have here is 10. So we now have that I2 will give us V all over R, which will give us V, the same PD here, 12 all over R. R here is just this one, just that 10, which will give us, this over this will give us 1.2. Therefore, total current in the circuit will give us I1 plus I2, which will give us that current is equal to I1 is 0.8 plus 1.2. 0.8 ampere plus 1.2 ampere. Therefore, current in the circuit will give us 2 ampere. And of course, this is option C. Option C is the right answer option. Now, the last but not the least, let's take it up. Now we have this question here, and this question says, in the diagram above, E is an accumulator with negligible internal resistance. Now, if the EMF of the cell is 9 volts, the total current in the circuit is this, or this. We solve it. Solution. If we take a look at what we have here, of course, this one is similar to the first question we solved, and this one will give us R in series plus R in parallel. Now, R in parallel will give us the, of course, R2, R1 times R2 all over R1 plus R2, which will give us this will be 5 times 20 all over 5 plus 20, which will give us 5 times 20, 5 times 2 is 10, that means 100 all over 25. Therefore, the resistors in parallel will give us 4 ohms. Now, if you come here, that means total resistor, which resistors in series plus resistors in parallel, which will now give us, that of series is 5 plus the one of parallel, which is 4. And if we add it to give us 9 ohms as our total resistors. Now, from Ohm's law, remember the current we have gotten here. We have the total current in the circuit, and then they say the total voltage in the circuit. Now, from Ohm's law, we have R is V is equal to IR. Now, with that in mind, make I the subject. I will give us V all over R. The voltage there is 9 volts all over the total resistance in the circuit, which is 9. And of course, 9 divided by 9 will give us 1 ampere. And then 1 ampere is option D. So the correct answer option here is option D. Okay, so this is where we draw the lesson to an end. Please, if you have not subscribed to the channel, do me this favor to hit the subscribe button, turn on your notification button, so that anytime a new lesson is uploaded, you'll get notified. However, there are so many questions that can be asked under electricity. To learn more, please join our online class. There is a link in the description below. Hit that link and join our online class, where we will introduce you to more options, more questions, and then how you can be able to wriggle your way out. See you in my next video, where I'll be treating cells. Thank you very much.